So first, hello everyone, and good morning. My name's Eric, and today's talk is titled, We're Not in HTTP Anymore, Investigating WebSocket Server Security. This talk's going to be split into three parts. First, we're going to talk about how WebSockets work, a bit of background for everyone. Next, we'll cover a summary of past WebSockets security research. And then finally, we'll get to this new STUs tool, which is released today. But first, a brief bio. My name's Eric, as you know. I'm a security researcher and consultant at Palindrome Technologies. Pen testing, telecom systems, web apps, Kubernetes, and more is a typical day for me. Previously, a security engineer at General Motors, working on securing vehicle modules, a lot of Bluetooth there. OSCP certified since 2019. I finished school and more on my website. Now, to the main presentation. Let's get into how WebSockets work. So the WebSocket protocol was created in 2010, 2011 with this single RFC, 6455. And the goal of the creation of this protocol was to provide a low overhead web protocol for real-time communications. And I want to mention this now, and I'll touch on it more later. The WebSocket servers are often distinct from HTTP servers. We'll get into that. First, let's compare WebSockets to HTTP. If you're familiar with HTTP and its encrypted and unencrypted forms, WebSockets work in a similar way. We have unencrypted WS and encrypted WSS. Going a bit further, WebSockets don't really use the request response approach that HTTP does. WebSockets remain open until they're closed, and these sessions can last for hours or more. This allows a web page to update without a refresh and even to get new data without JavaScript, which is a unique property of WebSockets. One note is that web proxies are generally, or at least were generally, built for HTTP originally. And the long session time for WebSockets can lead to problems. And those are known issues. HTTP does have headers, which adds overhead, but WebSockets don't. And again, because WebSocket protocol is created for real-time communications, that's by design. So anyway, WebSockets, a lightweight protocol compared to HTTP. Let's look at the WebSocket stack on the left. We can see that the WebSocket layer is pretty much a drop-in replacement for HTTP, occupies the same location in the stack, and you can even have protocols on top of WebSockets. On the right, we see a WebSocket frame, and the green section is the payload data. And you can see that that's the majority of a WebSocket frame. So we're really focusing on the data with minimum overhead. To mention briefly, there are actually protocols that can be implemented on top of WebSockets. As far as I know, there hasn't been any security research on this topic. And unfortunately, we won't be touching on that today. But just to list a few of the protocols that can be found on top of WebSockets, these are a few. Let's dive into an example WebSocket connection, just so we can actually see what's going on. Now, step one on the left is that an HTTP request from the browser or other client is sent to the server. And you'll see in the screenshot that there's a lot of instances of the word WebSocket in this request. And that's by design. That's part of the WebSocket protocol. And then on the right, we see a response from the server. It's actually got a status code of 101, switching protocols, which is a relatively rare HTTP status code. And the reason for that is not many protocols use HTTP to jumpstart a separate protocol, but that's how WebSockets are designed. So a key point here is that in phase one of a WebSocket connection, we are actually using HTTP to start the WebSocket protocol. It's just that in the first phase, we don't actually have the WebSocket protocol. We have the HTTP protocol. In phase two, we have the WebSocket data being sent. And honestly, there isn't a whole lot to see here because, again, WebSockets are focused on the actual data and not on the overhead or headers, unlike HTTP. This is just an example of what you might see with a chat application running WebSockets. Where are WebSockets found in the wild? There's quite a few applications and they are growing. Keep in mind this protocol is only 10 years old, which compared to HTTP is pretty young. We have a lot of use cases, including chatbots, chat solutions with other humans, usually, maps that have real-time updates or movement, live finance data websites, especially graphs, same with cryptocurrency websites, and a couple more unusual use cases include a smart TV remote control and even the Kubernetes Docker API. So we're going to do a quick demo. You can follow this at home, kids. Yeah, this is actually safe to try home, so feel free to follow along. So if you want to open up a web browser, and then inside the web browser, you can open up the developer tools. Shortcut is Control-Shift-I, or you can find it in the menus. And then within developer tools, there's a network tab. Now in the network tab, I know we're getting deep into the developer tools here. There's a WS button, which stands for WebSockets. And if you click that, the browser will start filtering for the WebSocket traffic. I've listed a few example websites here based on the different applications or use cases for WebSockets. So you can visit whichever site you'd like. And after the web page loads, you'll actually see some WebSocket traffic in your browser developer tools. Of course, web proxies like Burp Suite and OWASP Zap will also capture this traffic. But do note that these tools actually show the WebSocket traffic in a separate tab from the HTTP traffic. And just to clarify what I was talking about on the previous slide, I have a couple of screenshots here. In the first screenshot, we see the Firefox web browser developer tools. There is that WS button to filter the WebSocket traffic. And then for Burp Suite, you can see the WebSockets history tab is separate from the HTTP history tab. Great. So hopefully that level sets everyone to have a bit of background for what WebSockets are, a little bit about how they function, and now we're going to dive into a summary of the past WebSocket security research. To be quite honest, there isn't a whole lot to cover here, which is part of the reason for this talk. I've highlighted perhaps 3 of the top events in WebSocket security history. So in 2011, keep in mind the WebSocket protocol was created right around this time. Firefox 4 actually temporarily removed WebSocket support due to a protocol issue. I would like to point out this was before the WebSocket protocol was finalized in its current form, but it does show that there have been security issues with the protocol for a while. In 2016, 5 years after that event, a blog post is published describing cross-site WebSocket hijacking, which is a mouthful. But all it says is that the HTTP CSRF mitigation cores doesn't apply to the WebSocket protocol. And that means that if web developers are using WebSockets and they're not aware of this, they might assume that they are protected, but in fact, that protection doesn't apply to WebSockets. You have to perform a separate mitigation specifically for this protocol. 3 years after that, in 2019, a talk is published describing specific attacks against web proxies, reverse proxies that don't properly handle WebSockets, which can lead to WebSocket smuggling. And I wanted to highlight this. It's not a specific research event, but it is certainly an event in WebSockets history. Last year, there was a lot of press around eBay port scanning systems when you load their web page, and that was done over WebSockets. At the bottom here, I have a screenshot from a slide deck with the link for the slide deck describing a bit more about port scanning with WebSockets. So again, a known issue, and one that, as we saw last year, can have real-world consequences. For those who prefer the visual format like myself, this is just a quick timeline of WebSocket security research history. Again, the key point is that there hasn't been all that much when you compare it to a protocol like HTTP, which appears to get all the attention. The red text and the red events, these are related to a similar topic. It's not actually WebSocket related, but it is related to that 101 response from the server, the HTTP 101 status, which is also used for HTTP 2 when you transition from HTTP 1. Okay, so quick takeaways from past research. I guess at a high level, there hasn't been a lot of large-scale security testing of WebSockets in the wild. It's sort of been specific use cases, specific scenarios, and often focused on the protocol level, and then more recently on the proxy mishandling of WebSockets. So the question remains, what about the server implementations and the security there? It does appear that HTTP gets all the attention, and just to drive that point home, perhaps some listeners have seen a graph somewhat like this, or are simply aware of some of the top HTTP servers that are out there. At this point, Apache, HTTP, and Nginx are probably the top two. And the interesting thing is we have this data going back for 2+ decades at this point for HTTP servers on the web. The thing is, we don't really know what's going on with WebSocket server implementations. It's kind of a question mark, and I'll get into perhaps why that is in a moment. Now, if you remember, I was talking earlier and more recently about how WebSocket servers are distinct from HTTP servers. This slide sort of shows an example of that. These are some of the most popular WebSocket server implementations, along with the programming language they're built in. And I guess you can read through the list on the far left column. I don't know how many names of these servers are familiar to listeners, but based on the far right column, the GitHub star count, which is pretty much all we've got in terms of data for what the most popular ones are. Obviously, developers are using these servers. It's just we don't have much data on where they are or how they are used in the publicly accessible internet. So that is what we will get into shortly. I'd also like to mention real quick, the previous slide showing the top HTTP servers. I would say the majority of the market share is really split between maybe 3 or 4 HTTP servers. But here we can see it's not really that dominated in the WebSocket server market share. It really is sort of split up by what's your preferred programming language for the backend system. So just an interesting observation. Okay, now we are jumping into the more interesting and new part of this talk, which is the STUs tool or tool set. So first, like to say who doesn't like free stuff? These tools are released today, fresh out of the oven. I will leave this slide up for a brief moment so you can pull up the URLs that you'd like, get the repository. The first link here is the actual repository for the STUs tool. That also includes a white paper and this slide deck, so you can have a copy. Second repository is the WebSockets Playground. It's a way that you can quickly set up a bunch of WebSocket servers for local testing on your system. And lastly, we have the WebSockets Security Awesome, which is a compilation of security research on the topic of WebSockets. So I'll leave this here for a quick sec, grab a drink of water, and you can open up the links. Okay, great. Moving on. So what is the point of this STUs toolset that's just been released? To be quite honest, I was hoping such a toolset would not be necessary. I was hoping that when I'm encountering these WebSockets in my testing, I could just pull an existing tool off the shelf, use it, and it would already have the features I was looking for. It turns out things aren't that simple, unfortunately. And again, I blame that on HTTP getting all the attention. So I've listed a few great tools here. It's just that unfortunately they lack in this very specific niche of customizing WebSocket server test cases. The first, Nmap, a great all-around tool. Unfortunately, the post in 2015 offering the idea of WebSocket support did not get very far. As for Burp Suite, it actually does support WebSockets, which is fantastic. Unfortunately, it does not support WebSockets for extensions, which is how you can customize Burp Suite. Lastly, Nuclei. It does appear that there is some progress on this open issue, but it's not yet closed out, and it's unclear when that will happen. So again, these are great tools. It's just that unfortunately in a small niche, it doesn't appear that they've gotten to implementing custom WebSocket test support yet. I hypothesize that's because WebSockets, again, just like the issue with web proxies, these tools are built for HTTP, and supporting long duration WebSocket connections probably requires some redesign of the underlying tools. So again, we see the difference between HTTP and WebSockets rearing its head. So STUs is, let's say, a clever acronym for security testing and enumeration of WebSockets. And it's designed to do three key things. The first is to allow for the discovery of WebSockets endpoints. The second is to perform fingerprinting, which will tell you a bit about what's going on with the backend WebSocket server. And the last is vulnerability detection. So let's dive into these three key features of the STUs toolset. The first is WebSocket discovery. And this is actually rather hard. And I'll try and explain why it's hard. In fact, first, as a thought experiment, I'm sure if I asked you to provide me with the endpoint of an HTTP server, you would have no problem listing out any number of URLs that you visit frequently. However, if I was to ask you for a WebSocket URL, I would bet that the majority of the audience would be stumped by that question, at least off the top of their head, unless you remember the slides I showed earlier that had those URLs. Now, the first reason why WebSocket endpoint discovery is hard is that, as we saw, WebSockets use HTTP to start a connection. But if you see HTTP alone, it doesn't mean that you have a WebSocket. Often, HTTP is just HTTP. It's not allowing you to create a new WebSocket connection from it. The second reason WebSocket endpoint discovery is hard is that WebSockets often start WebSockets with websites often start WebSockets with JavaScript. So you can't just look through the HTML, let's say a spider, and quickly pull out, oh, here's a URL, there's a URL. You actually have to render the JavaScript, which naturally, if you're spidering a large website, takes a lot of time. And then often, you can even find that there's no direct link to create a WebSocket connection from the main website. Instead, the WebSocket endpoint is a standalone URL, either a standalone API or for some other purpose that might not actually or the connection may never get created from browsing the main website. It's for, say, a custom client or a separate tool. And finally, perhaps, well, all of these make the process difficult, but the last one is that WebSockets might only exist at one specific URL path of a specific port of the endpoint. And if you're familiar with HTTP, you're often finding servers at port 80 for unencrypted, port 443 for encrypted. And that's often similar for WebSockets, but it's not always the case. And unlike a website, which often has many URL paths that make up the website, the WebSocket might only be at one single path. Just visiting the website and navigating half of it, you might still miss the WebSocket endpoint because it could just be at one specific location. So all of these factors combined make it difficult to actually find a lot of WebSockets on the internet quickly. And I would argue this is probably the top reason that we don't have great data on what WebSocket servers are currently on the public internet, because just finding them is a challenge. But that's what Stu's is here to help with, hopefully. So we just went through all these challenges, and I won't pretend that there's an easy answer to all of them, but there are a few approaches that you might think of in terms of how to solve these difficulties. So I broke this into two different categories. The first category is finding WebSockets on one single website or domain. And the second category is finding WebSockets on any website or domain. So if you're limited to a specific website or domain, so you're only testing, say, a specific domain for whatever reason, the most obvious solution is to spider the website, to try and look around, see if you can find a response from the server that is a status 101 response, which will often indicate WebSocket being started. So you could just look at the HTML and try and look for WebSocket keywords, maybe even look in the JavaScript code. But there's a lot of false positives if you're just looking for a keyword among text. You don't actually know if the connection exists at a certain endpoint. Now, if you are to actually load all the JavaScript and then watch all the responses, in that case, you're more likely to find a WebSocket on a specific domain. But the problem is it's a slow process. You're going to have to load quite a bit of JavaScript. At some point, you might just consider browsing the website manually. Yeah, I think the downside to this approach is that it's slow in terms of spidering a website. Now, if we don't care where the WebSocket is, if we just want to analyze WebSockets on the public internet, regardless of where they are, then we might try a different approach. We don't have to necessarily open every website, spider to every page, and load the JavaScript. Instead, we might be able to just use a word list of common endpoints and brute force a large list of website domains. Of course, this approach has its own downside, which is that you're only testing the word list endpoints. The positive perspective of this last idea is that it could be fast because we're not spidering each website. We're just testing a few key likely locations on a large number of websites. And it is this last approach, as you may have guessed, that was chosen for the Stu's discovery tool, primarily because it's easily scalable to a large number of websites across the internet. Okay, so we've chosen an approach. Are the difficulties all handled? Not quite yet. We still have a few. So the first difficulty is, how do we do this scanning? Let's say we have a long list of domains. How do we know if any of them have WebSockets? So you may have heard of tools like MassScan or ZMap that have done internet scale port scans and mapped the internet, so to say. Unfortunately, these tools work at the TCP/IP layer, and we need to go a layer above that to HTTP or WebSockets. Now, again, these tools would be great if finding an open port was equal to finding a WebSocket server. But even if we find an open port on port 443, it could just be an HTTP server. We don't know if it supports WebSockets. So those tools won't work, at least without heavy modification. Now, option number 2 is Burp Suite's Turbo Intruder. We know that this can do fast HTTP traffic communication. Now, the difficulty here is that the turbo intruder documentation itself states that it's designed for sending lots of requests to a single host. Now, we want to do the opposite. We want to send a few requests to many hosts. Now, fortunately, the documentation there does suggest an alternative for what we want, which is zgrab. And zgrab 2 provides fast application layer scanning. However, it does require a few tweaks to support WebSocket requests. And there is a separate zgrab 2 fork that was used for this testing, which is mentioned in the existing repositories. Okay, so we've got a tool. It can scan many websites for potentially 101 status, HTTP status responses. That's great. Now we need to find the targets that we are going to scan. Now, the first option here is to just Google top million URLs. I have a let me Google that link for you to make it easy. But a second option, which would perhaps be a more thorough alternative, is to use zone files. Now, zone files are effectively what DNS servers use to map domain names to IP addresses. So in theory, this is a more comprehensive list of, say, all of the .com top-level domains that exist, or .org. The downside is that, unfortunately, many of the URLs in the zone file are not actually active, so they're sort of dead links, if you will. And additionally, the .com top-level domain file is a text file that's over 20 gigabytes. So you're handling very large amounts of endpoints in that case, and it might be easier to just start with a few million URLs instead. Okay, so we have a tool, and we have a list of endpoints. Are we done yet? Not quite, unfortunately. There's still some difficulties, as was experienced during this testing. If you've used a tool like MassScan or Nmap, often when you're doing a port scan, you're using IP addresses. Now, in this case, we are not using IP addresses. We are using domain names, which means in order to get the IP address of the endpoint, which is what the computers actually need to talk to each other, we need to perform a DNS lookup. And if we have a list of millions of domains, we're going to need a lot of DNS lookups. And that process can be a bottleneck. So during this testing, it was discovered that a lot of DNS servers do have a rate limit. You can partially solve this issue by using multiple DNS servers. The details of that are in the repository documentation. And additionally, one way to speed things up is that zgrab 2 actually allows DNS lookup beforehand. So you can use a purpose-built tool for looking at DNS servers and then provide the outputs of that tool to zgrab, which will save time later in the process. And an additional note here is that the DNS lookup process took about half the time of the total scan. So if you do run this process beforehand, you can cut your scans in half in terms of duration. Okay. DNS lookups solved. Next step is getting a word list of likely WebSocket paths. Now, there is no word list that you can just download for this because, again, this process hasn't really been done before. So this word list was gathered manually through, say, random browsing, looking for bug bounty reports mentioning WebSockets, looking at GitHub repositories that have a lot of WebSocket endpoints. And after going through all this manual process, we can finally find likely locations where WebSockets exist and automate the process. So finally, I'd like to present the first large-scale data set of WebSocket endpoint discovery. And this table demonstrates the word list used to attempt to find the WebSocket endpoints. As you can see, the numbers speak for themselves where the most likely locations are. It does appear that just on the homepage of a website, without any additional path, is actually the most likely location to find a WebSocket, followed by the /WS path. I will say that the reason most the top visited websites will not have this configuration because those websites are much larger. They can locate their WebSockets in other places, perhaps more hidden. So most likely the large numbers for these first few results come from smaller websites. And again, the data set is about 3 million domains that was scanned, and the total of 12,819 WebSocket servers doesn't mean these are all unique servers because there is some duplication among the results. But if we do the quick math of assuming those are unique, it's about 0.4% of websites or of domains that have a WebSocket endpoint. And that's most likely a low estimate because, again, we're simply brute forcing less than a dozen endpoint paths right here to try and find the WebSockets. So there's almost certainly many more hiding out there that we have not yet found. Okay, that concludes the discussion of the discovery process. We now can say we can go out and we can grab a list of WebSocket endpoints to analyze. Great. And I have a quick demo video here. I hope the demo gods will play nice today. So we're in the Stews repository. We're going to the discovery folder and we run the tool. And there we go, we have results. Now these results are gathered from a file provided of known endpoints. So we would expect to find WebSocket servers among these known endpoints. And the 101 being printed out indicates the HTTP status code, which is most likely indicative of a WebSocket server. Great. So that's just a very brief demo. Again, the tool is online. You can play with it yourself. You can plug in your own domains, subdomains, you name it. Great. Now, on to the next stage, WebSockets fingerprinting. So the challenge is to find implementation level differences between these WebSocket servers to try and identify them. So for example, if you've done this with HTTP, you might use an HTTP header in the server response that says Nginx or whatever other server is running. Now, sometimes this does exist for WebSocket servers, but often if the server is hardened, that header is removed, and you have to be a bit more clever with how you detect the server. Now, in theory, this process shouldn't really be that easy or even possible, because in theory, everyone is following the WebSocket standard. But as we know, the great thing with standards is there's so many of them. And additionally, there's a lot of portions of the WebSocket standard that are not really covered in the standard, but occur in the implementation process, often through non-standardized means. Now, just to remind the audience of some of the top WebSocket server names, this shows also that these implementations are in different programming languages. These are just a few of the WebSocket servers, but there's dozens out there. And as we covered earlier, there isn't really say top 3 servers that are the leading market share among all WebSocket servers. It does seem like things are a bit more mixed in terms of many servers existing on the internet. So we have some work ahead. So if we compare the Stews fingerprinting tool with other fingerprinting tools, pretty much all HTTP fingerprinting tools only have to handle HTTP. But in this case, remember that WebSockets actually start using HTTP before the WebSocket protocol is used. So that means that the Stews fingerprinting tool actually is handling 2 different protocols for the fingerprinting process. And then the second difference is that tools like Nmap or others can actually query different URL paths to try and figure out what's going on with the back end. So perhaps an error page will actually tell you what the name of the server is. But keep in mind that WebSocket servers are usually only at a specific URL path. So we can't really do that. We can't navigate it like a website. It's just one URL path, and that's pretty much all you've got. So less information we can gather there. In order to actually find out how WebSocket server implementations are different and find identifying features, I used a simple deterministic fuzzer to test different parts of the WebSocket frame, different features of the WebSocket server. And this lists a few. If you want the details, check out the tool documentation. But for instance, WebSocket protocol version number can be changed, and sometimes certain implementations will support version number 8 or version number 7, in addition to the most recent one, which is version 13, but others will not. Additionally, there is reserved and opcode bits. This is the closest equivalent to a header that you have in a WebSocket frame. And if you set these special bits, servers react in different ways, most often with an error message, which can be rather verbose and actually give you information on what's going on back there. The last identifying feature mentioned here is the maximum data length. So by default, a lot of these servers have a maximum length of the WebSocket frame built into the source code. And of course, this value can be modified, but again, often it is not, and that could be used as an identifying feature. I'm not going any further into the details because there's actually 50 or over 50 different tests used for this fingerprinting tool. I've split them up into 7 categories, if you will, and this gives a little more detail on what's actually going on with each one. And on the far right, you can see we're actually dealing with both the WebSocket protocol and the HTTP protocol in an attempt to fingerprint these servers. I've zoomed in on a single test case here just to show you the differences between different implementations. So here we're looking at test case 200 of the STU's fingerprinting tool. And on the far left, we see the names of the WebSocket servers. And on the right, we see the error messages given by each server. Now, again, these are default values. They may be changed in different implementations, but frequently it was found on these public servers on the internet, a lot of the default error messages remain unchanged. And this alone, as you can see, these are very distinct error messages for each implementation. And this single test case alone might be able to tell you what's going on the back end. Okay, we have a demo. Now, this demo is of a local server. So we're in the STU's repository. We go to the fingerprint directory. And let's look at the help file real quick. We have some documentation. And this command here is going to test our local server with some of the test cases. Some of these take a bit of time because there's a lot of data being sent, or there's a timeout that we need to wait for. And at the end here, we have a lot of data, which is showing the fingerprint information. And we also have an answer for the most likely server, which in this case is Gorilla, with a very good match. Now here, we're going to run the tool again on the same local server, but now I've disabled the debug output, so things are at least a bit cleaner. And we're just going to get the results at the end of the test, which are the same as before. Very good. So that was a local server, but of course, we want the exciting stuff. We want a public server on the internet. So we have another demo. So using that known endpoints file from the discovery portion of the tool, we can scan one of those URLs because those URLs specifically were chosen because they have bug bounty programs. So in theory, we should be okay testing on them. So here we're seeing some slightly different messages from the server. And that's likely because it's a custom implementation of some sort on the back end for at least parts of the communication. And keep in mind here, we don't actually know what's going on with the backend server, so this is our best guess. So up here, if we see the fingerprint received, and if we look at some of these outputs, we can actually see that there's, say for test case 200, which is the one we had an example of in the slides, unexpected reserved bits, 0x10. And for the most likely fingerprint, which is Gorilla, for test case 200, we have unexpected reserved bits, 0x10. So again, just this single test case alone is likely an indicator of what's going on with the backend server. And this information can tell us what programming language the backend server team likes to use. We can perhaps check if there's CVEs on the specific server, and it's just a lot more information than we had previously. I would like to mention that the matching percentage here, don't put too much faith into it. It's a very simple algorithm that should probably be improved in the long run. Okay, so we have fingerprinting. We can see the output of the fingerprint. You can also add new fingerprints if you have servers that you know what's running on the back end and you want to integrate it into the tool. And then we can run the Stu's fingerprinter and get some information about what's actually going on with these servers that previously we possibly couldn't even discover them in the first place. Now, we are at the final stage of what the Stu's tool can offer, WebSocket vulnerability detection. So these WebSocket servers that are out there, they have a few CVEs. You can see this table of a few, but there's actually a longer list in the repository, the WebSocket Security Awesome, which again is released today with this talk. So if you want more information, you can go there. I also have links in that table to the package that's vulnerable and some of the write-ups that you can get, sometimes with proof of concept code for checking if it's vulnerable. Okay, so if we're trying to detect if a WebSocket server is vulnerable, ideally we would have a way to test this without actually using any exploit. But unfortunately, at least for some vulnerabilities, there aren't really many other good ways to check for this. Currently, the Stu's vulnerability detection tool only includes a few checks for a few CVEs. And in fact, most of these are regex denial of service vulnerabilities, the CVEs listed here. And hopefully we'll add more of these in the future. Now, I'm not going to go into detail much more on this part of the tool. In theory, my hope is that if some of these other top web security tools integrate WebSockets into their tool set, this vulnerability detection portion of the Stu's tool set will probably be the first thing those other tools implement. So let's hope that they get to that stage. Now, again, we're in the Stu's repository here. We go into the vuln_detect directory, and we can see the help file giving us some information, what we can do. And we're going to run this test on a local server, first one that's not vulnerable to any CVEs. And here we're only testing for a specific CVE. And then we run it on a local server that it appears is vulnerable. So we get a negative result for the first and a positive for the second, or vice versa, depending how you look at it. And we can, in theory, state that the second server is in fact vulnerable to the CVE. Okay, wrapping up a few minutes early, luckily. So a quick summary of this talk. In part one, we talked about how WebSockets work similarly to HTTP, but they're designed for lower overhead real-time communication, and they're also less examined, at least in the security world, possibly because they're harder to find, at least until today. Part two, we discussed the past security research on WebSockets, and the takeaways were that there's been relatively minimal research done around WebSocket security, at least when compared to other portions of web app security. Unfortunately, it does appear too that popular tools for web security lack support for customized WebSocket testing. Hopefully that will change. And then in part 3, we went through the features of the STUS toolset, which is released as of today, and saw how the toolset now provides off-the-shelf tooling for discovering, fingerprinting, and detecting vulnerabilities in WebSocket servers. And as if we aren't already getting to a lot of WebSocket security today, I have some ideas for any audience members who would like to take this further. Because again, WebSocket security research has not been the most eventful of areas in the security world. I do have many more ideas for research mentioned in the white paper, which again is in the STUS repository. But just to mention a few, the WebSocket protocol allows for sub-protocols designed as within the WebSocket protocol, and then additional protocols on top of WebSockets. So these really haven't been explored, and it might be an interesting area to look at, depending how frequently used they are in the wild. Second idea is that there's an additional RFC, 7692, which I believe was released in 2015 or 2016, which handles WebSocket compression. And this is implemented by some WebSocket servers. Not all the implementations support this RFC, but it allows for sending larger files over WebSockets. And because it's a newer RFC, I suspect there has been much less focus on looking into implementations here. Third idea, if we go back to the STUS discovery tool and how it works through brute force. It's not looking at a specific single domain and analyzing it thoroughly. If we had a tool that could do that, we might be able to find more WebSocket endpoints when we're only testing one domain. And we would also get more information where WebSockets are hiding, which URL paths, what features they offer. And that would inform the STUS discovery tool, the brute force approach, by giving a better word list. And then lastly, because as we saw, WebSockets rely on HTTP to be first initialized. It might be possible that these WebSocket servers have HTTP type weaknesses that have been solved in the very big name HTTP servers like Nginx or Apache HTTPD. We might still have those weaknesses in these WebSocket server implementations. So again, the white paper has more ideas. If you'd like to read more about WebSockets beyond just what this talk offers, these are a few suggestions. And the WebSocket Security Awesome, also released today, has a lot more links. And with that, we've made it to the end. Thank you very much for joining me, and I'll pass it back to the moderator.